Good evening, everyone. Today we will continue with the second lecture, the first part of the second lecture of your course of Introduction to Measure Theory. So, the starting concept or the main concept of today's lecture will be measures. So, this will be measures. Recall that in the previous lecture we talked about measurable spaces. So in those measurable spaces, we will define measures. So for some measurable space, let's say we have this is the space, which is also a set, and this is its sigma algebra, which you know that any given set can have a number of different sigma algebras. You just pick one, and then this makes it a measurable space. So from here we will define a function that is called a measure, that we usually write with this symbol and sometimes with this symbol, which is once again which can be many functions. I mean, you can pick one of those measures and then from this measurable space you go to a measure space, which will be, this is a you have two terms here, and then a measure space you have three terms. It's a triple, right? So we will formalize this, and to do that we start with our main definition, and that will be, let's say that we have let X and A be a measurable space, a function that goes from the sigma algebra into this interval. So this function can have this value, which is a plus infinity. So this is a subset of the extended real line, right? So this is called it's called a measure, or also known as a positive measure. If and only if this function is completely additive. And this concept AI, this concept means that for every family that is pairwise disjoint, so this is some family in the sigma algebra, of course, we have that the function evaluated in the countable union of these elements is equal to this series, to the value of this series, right? And this is it. So this is a key property. So if this holds for every family that is pairwise disjoint, so this means that for every, let's say we have two different indexes, then this intersection is the empty set. So this is the meaning of pairwise disjoint families, and so this is the property that is called completely additive. that this will be key. All right. So we call this triple, as I told you previously, a measure space. Well, if X is different from the empty set, A is a sigma algebra on X, and mu is a measure. In this case, it's a measure on. You can say that this is a measure on A, or just that is a measure. So we have the second definition of a measure space. So this is like a chain, right? We first define sigma algebras, then we define measures, and so now we have our measure spaces. So some remarks are in order. Let's write it here. Remarks. The first remark is that this sum is obviously and this is obviously a number that is non-negative and can be the infinity. So we are not saying that this series always converges. It may be a divergent series. It can have this value, but what cannot have is that this cannot be a negative number. So this cannot be a negative, because this is equal to the to this term here, and you know that our measure is always non-negative. So the value of this series when it converges can only be positive, and if it's divergent, then it should be the plus infinity. So that's our first remark. And the second remark is that it can be, well, for some measures you may have that for every element in our sigma algebra, the measure of this set is equal to plus infinity. So this is kind of a trivial measure. Because if you have that, then it's of course completely additive, because this is an element of the sigma algebra, so the value of the measure on this set will be plus infinity, because it's plus infinity in every element of the sigma algebra, and then this will be also equal to the value of this series, because you are assuming plus infinity with plus infinity and so on, so this will be also plus infinity. So this is our first trivial measure. So it only makes sense that we say that a measure is not trivial whenever there exists some element in this sigma algebra such that the value of the measure on this element is less than plus infinity. So it's completely sound to call this a non-trivial measure. Now, our another definition that comes as a remark is that if the measure of the whole space is less than plus infinity, then we call mu as a finite measure. Right, recall that the sigma algebra, our sigma algebra always contains the whole space. So this was the first property of sigma algebras, right? So for every measure, the value of the measure on the whole space will be either finite or it will be the plus infinity. So when this value is less than infinity, then we call mu as a finite measure. So this will also imply that the measure of every subset of X is finite. So we will see this in the following, but this is the definition of the finite measure. So the fourth remark is that, well, it's once again a definition, and that is that if the value of the space is equal to 1, i.e. that this is a finite measure, in particular that this value is 1, then we say that mu is a probability. It's a probability on X, on or over X. So this is another definition. A fifth remark will be that let's say that we have a family here, a family in the sigma algebra, such that this is another definition, such that the whole space is equal to the countable union of these elements, and for every k this value is finite. So whenever this happens, we call this measure as not as finite measure, but as a sigma finite measure. So it's useful to remember that whenever you read a sigma in some term, it will always refer to some infinite union or infinite sum and so on. So this prefix always remembers us that we will deal with some infinity. So this is a sigma infinite measure. This sigma finite measure. It doesn't necessarily imply that the value of X will be finite. It doesn't imply that. Because well, going by definition, this will be equal to the series here, and even though these even though these terms are finite, it doesn't necessarily imply that the value of this series is convergent. So it may or may not be convergent. So this may be the plus infinity or maybe finite. We don't know. But what we do know is that we have a kind of a covering of the whole space. This is kind of a cover, quotation marks, a cover. And the measure of each element of this cover is finite. So this is all we know. And when this happens, we say that mu is a sigma finite measure. So this is another definition that we will use in the following. Now let's go with an example. All right, let's say that we have a measurable space X and our sigma algebra, and we have some function that is defined on this sigma algebra like this. That is defined as follows: mu of A is equal to 0 for every element of the sigma algebra. Then it is trivial that mu is a measure, because it is of course completely additive. Because if you have a family, if you have any family that is countable and is pairwise disjoint, disjoint. Then the union of this family will be an element of the sigma algebra, so this value will be 0. And on the other hand, the series of the value of this series will also be 0 because each of these terms is 0. So they are equal. So this means that the function is a measure because it is completely additive. So this is our second trivial. This is the second trivial measure that is called the null measure. So it's like the opposite of the first trivial measure. We had that. Yeah, here. This is the first trivial measure. This measure. All right. So this measure gave plus infinity to every element of the sigma algebra, and now this measure gives 0 to every element of the sigma algebra. So it is equally trivial. And the next example, example number 2, will be that once again we have a measurable space here, and we have a function that goes from here, and the measure of the empty set is 0, and the measure of A is equal to infinity for every A in the sigma algebra that is different from the empty set. So it holds that mu is also a measure. And why is that? Well, because in this case it is like it is a little more elaborate. Now we have two values. But let's say that we have a family that is pairwise disjoint here, and we have its countable union like this. So if this countable union is equal to the empty set, then this means that each element is equal to the empty set. So the value of this union will be 0 because this is the empty set. So check mark here. And on the other hand, the value of this series will also be 0 because each term is equal to 0 because each A sub k is the empty set. So they are equal, and that makes it additive. Now you have another scenario in which this countable union is different from the empty set, different from this. So if this happens, then the value of the measure on this union will be plus infinity because the second case. And on the other hand, this also implies that there exists some term such that is different from the empty set. Right, because if everything was the empty set, then the union of empty sets is just empty. So necessarily some element will be different from the empty set, and so the value of this measure will be plus infinity. So when you make the series, this will be necessarily plus infinity because one term of the series is equal to plus infinity, and the rest are positive numbers or plus infinity. Are 0 or plus infinity. So when you assume plus infinity with 0 or with plus infinity, it's plus infinity again. So they are once again equal. So in every case, the function is completely additive. So that means that it is a measure. All right, it is important to recall that this is only this equality it is necessarily to hold only for pairwise disjoint families. So if you have a family that is not pairwise disjoint, it may not be equal. It could be less, strictly less. And that doesn't make it less of a measure. It is still a measure if it holds for pairwise disjoint families. So this is it is everything that we need to show. In these cases, it is so trivial that we don't need to really consider if this family is pairwise disjoint or not, because the simplicity of the example. But on more complicated examples, you will need to really take care of this condition. So this is this is example 3, our third example of somehow trivial measure. Now, moving on. There's another example of a measure that you can check on your own, that is a measure, and that is the following. Let's say that X is an empty set. Recall that this is a necessary condition to associate a sigma algebra with this set. The sigma algebras are only defined for non-empty sets. So we have a non-empty set here, and we have its power set. So in the first lecture, we reviewed that this was a sigma algebra, a trivial sigma algebra of X. And that is, of course, the biggest sigma algebra that you can associate a set with. So we have then X and its power set. This is a measurable space. And then we have a function that goes from the power set into this extended interval and is defined as follows. So for every A in the power set, this is either the cardinality of A when A is finite, or plus infinity when A is infinite. So you can check this on your own, but this is also a measure. Well, I do want to comment on a couple of things, and that is that to check this, to check that this is completely additive, you will need to consider, in this case, pairwise F disjoint families. So yeah, and of course, the reason that we are defining this as a plus infinity for infinite sets is that we cannot have the cardinality of infinite sets here, because the cardinality of the infinite sets is not the symbol, but this goes with LFs. So it could be a left 0, it could be a left 1, and so on. So this is Cantor's transfinite sets, right? But we don't need this precision. It only suffices to have plus infinity for every infinite set, no matter how big this set is, and we will have a measure. All right. And finally, I mean, I don't want to prove this example, but perhaps you're a little confused with this infinite sum, with this infinite union. And by that, I mean that you may think that since this family is pairwise disjoint, then this union, since it is an infinite union, then it must always be infinite. And this is not true, because in this infinite family, many elements could be, infinitely many elements could be the empty set. And so yeah, these sets are equal, but sets, empty sets that are equal are also pairwise disjoint, because the intersection of these two elements is still the empty set. So you may have a case in which there are only finitely many non-empty sets. Let's say we have 3 empty sets here, 3 non-empty sets here, and the rest is just the empty set. So when you compute this union, it will be finite and you go by definition. And otherwise, if there are infinite non-empty sets, it will be infinite. So yeah, I think this is almost a proof in the example. So yeah, moving on, we have another concept that we want to show, or well, perhaps another example. Yeah, let's go with another example. So let's say that we have a measure space here, and let's fix some element of the algebra, and we will consider this set. So we are making another set out of the sigma algebra, and this set, its elements are the intersections of every element of the sigma algebra. So it is interesting that this is in fact a sigma algebra, but of A. It's not a sigma algebra of X, but of A, and that it can be clearly understood because you won't have X in this as an element of the sigma algebra, because X will be intersected with E. So the intersection, since E is a subset of X, this will be E. Unless, of course, E is equal to the whole space. But in every case, this is the sigma algebra of this set, and you can have a measure L like this. That goes from here into the extended interval, and this triple will be a measure space. So why is this happening? We can take a moment to consider this. Now let's work this example with all the steps. So let's first prove that this is a sigma algebra on E. So you need to recall that, well, the first definition that we cover is that A should be different from the empty set. So working on this assumption, because it otherwise, well, let's put it here. Otherwise, this will be just this set. So this doesn't make any sense. So given that this is non-empty, we need to check that E is an element of the set, which, as we saw previously, is indeed the case, because E is equal to X intersected with A, and X is always an element of the sigma algebra. So this holds. The second is that, let's say we have 2 elements for every A and V that are here. We wish to prove that the difference is still here. So if they are here, then you can write this as A prime intersected with E, and V can be written as B prime intersected with E, and A prime is an element of the sigma algebra, and this is also an element of the sigma algebra. So you need to remember here that for sigma algebras, this is also an element. For sigma algebras, intersections are closed in the sigma algebra. So every finite or countable infinite intersections are held inside a sigma algebra. So this is an element of the sigma algebra. And so as elements of the sigma algebra, its difference will be in the sigma algebra. But we wanted to have it here. So now we do a little trick here. So what happens when we intersect this difference with E? Does it change anything? Well, since A and V, well, let's write it here. Since A is a subset of E, because it is the intersection of some set with E, then this is a subset of E, then this difference is also a subset of E. So if you intersect this with E, this will be equal to the same set, right? Because it is a subset of E. And so this is equal. So we have that A minus V intersected with E is in here. So this goes by definition. Recall that this set is equal to the intersection of all of the elements of the sigma algebra. So when you intersect this element with E, it's the same element. So yeah, it holds this property. And the final property is let's say that we have some family in this set, and what happens with its countable union? What happens with this? Well, let's say that AK is equal to some AK prime intersected with E by definition. With this is of course an element of this. And so when you unite everything with every element of the sigma algebra, this is an element of the sigma algebra, and now you make the intersection of this element with E. But once again, given that each element it's we have that each element it's a subset of E, so the countable union will still be a subset of E, and then its intersection will be equal to the union, because this is a subset of this. So this will be our element. Once again, because this was an element of the sigma algebra, and given that this element is here, then its intersection with E will be an element of this set. But it happens that the intersection with E is equal to the same element, so we have this. And with this we conclude that this element A sub E is in fact a sigma algebra of E. So this is the first part. The second part will be to show that this new function is a measure. So for it to be a measure, we need to check that it is completely additive. So let's say that we have a family, a countable family here that is pairwise disjoint. So by definition of sigma algebras, its union will be here. So we can, since this function is defined on the sigma algebra, we can have we can evaluate this function here. And I'm telling you that this is a function because it is a restriction of a measure that is a function. Perhaps this is something that we didn't explicitly proved previously, that perhaps with some formality we will have to do it, but it is that mu is a function. So whatever association that you make is not necessarily a function. In the examples, it was quite easy to see that they were functions. But in general, any association that you make from some algebra to here won't be necessarily a function. So this is something that you need to check, that this is a function. So for this case, this is trivially true because this association is the restriction of a function to some subset of its domain. So it is a function. So we don't need to check that. Now we only need to check that it is completely additive. So let's work with that. So this is by definition then equal to mu of this set, and given that given that they are elements of, this here, as we have time and time checked, this is equal to some element of the sigma algebra intersected with this, that this is also an element of the sigma algebra. So this is in the sigma algebra, and this union is also in the sigma algebra. So this is well defined, and this will be equal to, since this is a pairwise disjoint family, this will be equal to this, right? Because this function is completely additive because it is a measure. So now this is equal to this here. Why? Because this a sub k is an element of this subset of the domain of mu. This is here. So we can conclude that this is equal to this. Now for the final part of this lecture, we will work a theorem. Let's write it here, theorem. This is the finite part of the lecture. So let this triple be a measure space. So it happens, it is a measure space that is not trivial, right? Not trivial. So by not trivial, I mean that it is not a first or second trivial measure. Everything is not equal to 0, it's not a null measure, and everything is not equal to plus infinity, that is the second trivial measure. Because in those cases, everything that we will enunciate will be trivially true. So let's work with these particular examples. The first is that the measure of the empty set is equal to 0. So for the first trivial measure, in which everything was equal to plus infinity, this is not true, but we are not considering that case. So this is the first property, and let's say that we have a finite countable family in the sigma algebra. Then it holds that this finite union will be equal to this finite sum. A third is that for every elements of the sigma algebra, if it happens that A is a subset of V, then this is true. And lastly, well, the fourth is that if, now once again you have two elements in the sigma algebra, and one is a subset of the other, and the measure of the smaller set is finite, then this happens. And the final property is this important property. For every, this holds in general. So yeah, let's work each property. For the first property, it's well, kind of trivial. We have that we can't work a family like this. Now better, let's work another family, and the first element of the family, it's an element such that this is finite and all of this is a sub 1, and for every other k that is different from 1, the measure of ak, well, ak is equal to the empty set, and well, the measure of this element we don't know. So this family, it's clearly pairwise disjoint because everything is the empty set except for the first element, which could be the empty set also, but let's take an arbitrary element of the sigma algebra such that its measure is finite. So from here, perhaps I will do it down. So yeah, let's suppose that we have that family, and so the measure of this, is finite, but it is also equal to the union with the empty set, and this is equal to the countable union, I mean of the first element, right? So this is equal to the countable union, and this is a pairwise disjoint family, so by the property of measures, this will be equal to this. So here, perhaps, well, you can avoid this step, and let's just put it bluntly like this. So this is equal to this because everything else is the empty set, right? So this is equal to this. This goes by definition of measures, but this measure is equal to the first measure plus everything else, right? And everything else is the empty set. So since these two terms are finite, this is finite. So they are real numbers. You can't fact cancel them out, so you will have that this series is equal to 0. And so if you have a series of constant terms and this series converges to 0, then this should be 0. Otherwise, for any other value, the series will diverge, right? That's clear. So we prove this here. For the second case, for the second property, this is kind of trivial. You only need to complete everything that follows from end. So you have this family, which is pairwise. I think I didn't write it, but this is pairwise disjoint. So you complete this family with the empty set. So you have a countable family. I mean, everything that follows from n, I mean n plus 1 and so on, will be equal to the empty set. So this is equal to the countable union, and then this is equal to a series infinite, but this series is equal to this plus this, and this is of course 0. So you have that property. For the third property, we use we will use the second property. I think, well, you can write it here. We have some set like this, then we can write b as b minus, oh well, a, and the union of a with b minus a, because this is a subset. So the measure of b will be equal to the measure of a united with the measure of this set. So this you have a family like this, a finite family. This is pairwise disjoint, so you can apply the second property, and this will be equal to from here the well, and since we had that, well, this is, I mean, this is here more or equal than 0. So if you have some real, let's suppose first that this is a, oh yeah, that if this is real, if this is a real value, then it happens that this is less or equal than this. So in every case, if this is infinite and this is infinite, then this is true. And if they are finite, then this is also true, because you know how the reals work, it's because each term is more or equal than 0. So if this term is infinite, so if this is plus infinity, then this term will be plus infinity, right? Because you have already plus infinity in one side, in the other it should also be plus infinity. So this also holds, because plus infinity is more or equal than any real number, and it is equal to plus infinity. So whatever this measure is, this relation holds. So in general, we have proved that for every case. Now, so that works the second. For the third example, for the fourth property, I think the only you need to do is you do exactly the same here, but since we under this condition that this is finite, then you can send it to the other side with a minus sign, because this will be a real number. So with this you have this property here. And for the final property, for the fifth property, this needs a little more work, but is kind of the same. You can make this union. Let's do a little drawing here. This is A and this is B. So we want to divide this in these joint parts. So this will be the first, this is the second, and this is the third. Kind of obvious what we will do. So this will be A minus B united with A intersection con B united with B minus A. So for each part here. And this is a pairwise disjoint family. So this is a finite pairwise disjoint family. By the second property, you know that this is equal to this plus the intersection plus this here. So and now we need to work the cases. We have in general that this holds, but it may depend on if it's final or final. I mean, let's work these cases slowly. The first scenario is that this is infinite. So this is kind of the smallest set, smallest in some term, because if this is infinite, then A is infinite, and I mean the measure of A is infinite, the measure of B is infinite, and of course the measure of the sum is infinite. And why is that? Because for every since this is a subset of this, then this always holds, right? So if this measure is infinite, then the fifth property will be trivially met, because you have infinity plus infinity is equal to infinity plus infinity, and that is trivially true. So this case is done. So the other case will be that this intersection is finite. So if this intersection is finite, what happens? Well, we can write this A minus B. This is equal to A minus A intersection with B, because the only part that when you consider A minus B, in fact the only part of B that makes any change is its intersection with A, right? So this is equal, A minus B is equal to this, and so the difference of these two sets, since the measure of the intersection is finite, then we go with the fourth property here. So A minus the intersection will be equal to A minus the intersection. And we do the same with the other one. So let me copy it here just to finish this proof. So this will be equal to A minus intersection, and this will be equal to B minus the intersection. So one of these cancels, and the other one goes to zoom, so you will have this is intersection, and this will be equal to this, and this is what we wanted to show, this. So this takes care of every property. Yeah, so the fifth property perhaps was the one that required quite of more work and think, but this is it. So if you have any questions, you can write it down in the comments below, and I will try my best to answer them. And so we will continue this lecture with part B, and that will be for tomorrow. So see you around.